Hello everyone, good evening. So I would like to start with Ansys portfolio first. I'll show you in high frequency what are the tools available, and then we'll show how to design or how to match the antenna using passive RF circuits. I'm sharing my screen. So in high frequency tools, we have Ansys HFSS, Ansys SI Wave, Ansys IcePack, Q3D extractor, EMC plus and charge plus. In case of HFSS, this is the high frequency structure simulator. It is used for designing antennas, metamaterial unit cells, or array of the antenna or antenna placement on different objects. Likewise, this kind of simulations we can able to do. So based upon the solvers, these simulations are we could able to do. Like suppose simple antenna we want to design, we'll prefer ANSYS FEM solver. Antenna placement on car. Suppose anyone want to design SBR plus shooting plus bouncing rays. These kind of simulations we can able to, or these kind of solvers actually we need to select when we are designing antenna placement on some object. Now we have a second tool, that is SI wave. In case of SI wave, you can see this is dedicatedly used for the PCBs, either it is single layer PCB or multiple layer PCB. Generally, if you want to find out signal integrity, power integrity, and EMIMC analysis also, SI wave plays very important role. In case of IcePack, this is again used for the thermal management part, where heat transfer or airflow. It is helping us to find out how this airflow is happening, heat transfer in IC packages, electronics assembly, and power electronics. We can able to see basically in IcePack. So thermal management part using CFD solver, we are doing in IcePack. Next one is Q3D extractor. Again, this tool is dedicatedly used for the PCBs only, either a single layer or multiple layer PCB. If you want to find out the inductance, capacitance, resistance, conductance value on that particular PCB, Q3D extractor is helping us to find out parasitic extractions values on that particular PCB. Next, we have EMC plus. EMC plus is mainly dedicated used for the cable purpose. You can able to see this is the outer line of cable, and inside that there are so many small cables available. In such a complex scenario, there is a high chance EMIMC loss will happen, and that we can rectify using EMC plus. Apart from that, we can do here cable harness, or also we can able to see crosstalk analysis of cables. Next tool we have charge plus. So charge plus is dedicatedly used for the charging and discharging phenomenon. Generally, this tool is used in aerospace and defense applications. It is simulates electric arcing in air surface and internal charging, particular transport and dielectric breakdown, helping the user assesses the manage risk and associate with exclusive charge buildup the system. Now, this is the overall workflow of ANSYS HFSS high frequency structure simulator. This tool is used for the 3D design. Suppose anyone want to design an antenna, simple microstrip patch antenna, then we'll first create a, we will check their parameters either using calculator, or we can do theoretical calculation and we can find out inductor length, width, height of the substrate, what substrate we are going to choose for design. Once that these parameters are ready, we will create a geometry over here. We will apply mesh on that. Based upon the electrical size of the geometry, we will here we will select the solvers, either FEM solver, IE solver, SBR plus, and DDM. And then we will apply operating frequency. We'll do analysis at what operating frequency it is working, and we'll run the simulation. So now there are two parts. One is pre-processing and other is post-processing. So here in the pre-processing, all designing steps will be considered, and in post-processing, we have results. We can able to see graphs basically in terms of return loss or gain or radiation pattern, etc. So this is the whole workflow. And here basically there are two parts. In case of HFSS, ECAD and MCAD. So in case of HFSS 3D layout, ECAD is considered for electronic computer aided design and MCAD is for mechanical CAD. Here we can design antenna, waveguide, filter, PCB connectors, wires, biomedical equipment, implantable antennas, and so on. Those are very new to the software. For them, ACT extension plays very important role. Here, go to HFSS antenna toolkit and we have to check the more than 21 types of different antennas are available over here, and we have to see which is the um, what basically we are doing in this toolkit. We are putting operating frequency. We will select what type of antenna we are looking for the design, and we will synthesize the design, and that geometry will be created, and then we will run the simulation. That is the whole process. Uh, After that, next one is SI wave. So SI wave, again, this is used for the PCB purpose. Either it is single layer PCB or multiple layer PCB. We can find out signal integrity, power integrity, thermal coupling of that PCB. We can able to identify EMI/MC analysis. We can able to identify. This is overall workflow of the SI wave. We will import the PCB layout, either it is ODBI++ file or any other software. We are designing these PCB layouts in Cadence or Zuken or Altium. We have to import that, then we will check, we will synthesize that, we will check validation of those. And once it is done, next step we can able to generate here DC analysis and AC analysis. In DC analysis, we have to we could able to see I squared of voltage value, current distribution, signal flow graph, thermal coupling with I spec, etc. And in case of AC analysis, we can find out AC impedance analysis, S parameter extraction, near and far field extraction, cross talk analysis, etc. These are the supporting file we required when we are importing into Ultim or Zuken, where Cadence, Zuken, ODPI++, IPC2581, and other ECAD formats like GD, .gds or .dxf, Garbal file, etc. We can do here full board analysis, where we can generate time domain crosstalk analysis or frequency domain crosstalk analysis. Also, we can able to do in Ansys electronics SI wave. So this is the other capabilities you can see on the screen, where DC analysis, power delivery network, AC frequency sweep, and electrothermal analysis we can able to do. This is the layout for SI wave. You can able to see this is the PCB tracks or PCB layout, where it is indicated with three colors, where first you can able to see green, and then second one is orange, and third one is red. So green indicates all signals are passing, orange indicates there is an error or warning, and red indicates there is a failure. So basically we will receive from this SI wave one PDF where NEXT and FEXT coefficients will be generated. This is the crosstalk time domain analysis, where you can able to see a near field voltages and far field voltages. And apart from that, we can able to see here I diagram analysis, or in basically we will convert into circuits, and we can solve those, and we can find out here linear network analysis, like SYZ parameter value, I diagram analysis, then touchstone viewing matrix reduction values also we can calculate. Apart from that, TDR and TD graphs we can generate from the SI wave. In case of power integrity, we can find out how much is the current at one particular point of the PCB, how much is the voltage, where is the excessive voltage, where is the minimum voltage, where is the maximum power, where is the minimum power, everything in detail we can able to see in case of power integrity. We can couple IcePack and SI wave for finding thermal management part. Same PCB we can able to use, and we can see signal integrity, power integrity, and further we can able to do thermal management part also after coupling with IcePack. This is the workflow. IcePack, this is again CFD solver. It is predicting airflow, temperature, heat transfer. Then PCBs, electronics assembly, and power electronics. You can see this is one case study. So this is the burned PCB. This is backside of PCB. You can see transmission line or tracks. Those are burnt tracks. So here in the right side, we can see this is the color indication from black to white. And as color changes, temperature is also increasing. Blue color shows approximately 66 degrees Celsius. Pink color shows 128 degrees Celsius. Yellow color shows 190 degrees Celsius. And white color shows the temperature value in between 253 to 284 degrees Celsius. And here electronic cooling applications you can able to see, we can either do it cheap and chip level assembly. We can able to analyze IC packages, board assembly, board plane assembly, system level assembly, or anyone want to design supercomputer room or server room. For them also we can put dimensions, or we can import this CAD and we can do thermal management, or we can check basically thermal management part, or we can check their airflow or heat transfer in that whole room. These are some other examples where we can able to see in first figure heat sink for fan. Second figure shows thermal conductivity map for PCB. Then third figure we shows this is the temperature counter and fluid streamlines for graphic cards. The next one is for LDP projector bulk cooling fan model with MRF fan model. And next example is about LED bulb. Basically, it is showing us temperature, and this is the animation of velocity vectors around the drone model. And in the last figure we can see this is the animation of particle traces through data center. So let's move towards today's design part. So we are going to uh, design. Basically we are going to match here antenna component using RF circuit, like how inductance, capacitance plays a significant role in this design. I will show you. So in this today's webinar, we are going to see 4x1 patch antenna array with feeding network which is operating at 10 gigahertz. You can see this is the layout of this antenna. We'll rotate this so that you can understand. This is the array antenna which is working for 10 gigahertz. Here we will see how to define EM sub design in a circuit and set its analysis. And second point, we'll see how to link HFSS and circuit design. And third point, we'll see push excitations. So basically already model we have designed in HFSS, and this is not exactly working on the given or expected return loss. So we can do changes, or we can match the circuit using ANSYS electronics. So you can able to see over here, this is um, the circuit level of the antenna which we have seen in ANSYS electronics HFSS. This is 4-patch antenna basically, and here uh, in this circuit you can able to see it consists of 4 microstrip branches. You can see here clearly 1, 2, 3, and 4. And these are built from circuit component libraries. Like these are inductance, capacitance values. Apart from that, these 4 patches modeled as microstrip lines. And port impedance is 50 ohm for this case also. So now we will next step we will proceed here. We will separate the patches. So we have to go to again in the ANSYS HFSS design. Just click on this 4 patches design. Go to layout editor. And here we are going to group this sub design. First we have to do isotropic. We have to group this. So select these 4 patches. I hope I'm audible to you. So first we'll group this patches. One, just press Control and select the remaining patches. We'll select the face. Once it is done, we have to just group that into sub design. And you can see here, after doing that, we are received the sub design. So one circuit group has been created for this all 4 groups which are available on the top. Did it finish? Suddenly, my call got disconnected. So now I'm moving towards the next process where we will define EM model and EM analysis of that sub circuit. I'll open the file directly. So here what we are doing, um, whatever grouping we have done for that purpose, we have created one sub circuit also that we will open here, and we will apply again EM analysis to that. So basically what I said, for this simulations, we have to check 3 points. One is to define sub design circuit and set up the analysis. Next one is to link HFSS and circuit design, and then apply push excitation. That's all. So you can see here in the second step, we have just selected here group into subsection where we have done these groups, and then after that in the circuit you can able to see these are the project in the project manager. These four and electronics patches or microstrip patches you can able to see over here in the circuit schematics. Next step is we have to define this EM model. So in the defining process, we have to go to this again project manager, and here whatever circuit we could able to see, here just double click on that. In that we have to find out here again U1 underscore EM circuit groups you can see, and here just right click on analysis and add HFSS solution setup, click on advanced, and after that we have to just cross check either it is frequencies 10 gigahertz is available or not. If it is not, type the 10 gigahertz, and then we have to click on this save fields and click on OK. Once it is done, the next step is to set this HFSS extensions, where in the solution setup we have to check here PML boundary condition, and here horizontal padding it should be 0.005, and vertical padding we are keeping 0.5, positive padding and horizontal padding 0.15. These two settings we have to do, and these are the array antenna where basically 4 ports will be there, where we have to check these voltages should be 1 volt initially, and later we have to just go to the solution setup where we need to do certain setups. So in that, just click on automatic align ports, and simulator HFSS should be selected. Then setup override should be setup 1, whatever we have done previous slides that we have to follow. And here we have to add next some solution setup. In that linear network analysis we need to choose DC, skip DC port cancellation calculation, and here add frequency 10 gigahertz. Only we are working for 10 gigahertz, only single frequency, that's why 10 gigahertz we have selected. And the last step would be push excitations. In the go back to the main design, and we have to click on the push excitations, so that in the push excitations you can able to see whatever circuit design, circuit level simulations like transit analysis we have done, that will be saved in the circuit, and whatever outcome is generated from this additional inductance, capacitance, radiation, inductance, capacitor, and uh, conductance values, that we can able to push back to the original circuit in HFSS. So that's why this push excitation will come in picture. Whatever uh, RF circuit or RLC values we have changed or we have added in this circuit, the same thing after getting this result, we can able to push back in the original HFSS design. So that is the main motto behind the push excitations. Here you can able to see these are the microstrip patch 1, 2, 3, and 4, and some R and C circuit, LC circuits basically added over here. So that's how this RF circuit will work. And once this push excitation is done, next step we have to check this whatever input voltage 1 volt we have given, it should be in that. In case of port 1, it should be PW into bracket port 1 magnitude comma frequency, and then we have for port 2, port 3, and port 4. Now apart from that, lastly we can able to see the gain graph. In that case, in case of ANSYS circuit, here itself we have to add far field setup, and for there are basically 3 points. 3D view we can generate and 2D views we can generate. In case of 3D view, if anyone wants to generate, then phi value it should be starting with 180 to minus 180, and theta value again from minus 180 to 180, and step size is 1. In case of radiation pattern 2D, in this case, first check phi value, keep minus 180 to plus 180, keep change starting, it should be minus 188, it should be ended 180, and in case of theta, you have to keep it constant. So theta value we have kept constant at 90 degree. So there are two planes, azimuthal plane and elevation plane. Again for elevation plane, keep phi value constant, keep start value 0 and stop and step value 90, and theta value just change -180 to +180. You could able to see the graph. So finally, after the matching after adding RF component at 10 gigahertz, we can able to generate the gain graph. So that's how we can able to see this kind of simulations in case of RF circuit, in case of matching of the antenna using RF circuit.